All right, everyone, welcome back. We are in the lab to perform the geometric optics laboratory. I've got the equipment set up for the first phase and the equipment for the second phase ready to go. Now we have three lenses that we're going to be experimenting with. One has a focal length of positive 10 centimeters. One has a focal length of positive 20 centimeters, and the other is a diverging lens with a focal length of negative 25 centimeters. We're going to be figuring out the focal lengths of these two lenses in two different ways, and then we'll be seeing how a combination of two different lenses works and whether we can accurately predict the results of that. Our first experiment in table 1 is going to be to figure out by what we call the parallel ray method exactly what the focal length of the lenses that we have are. Lenses, like many things, are built with a manufacturer's tolerance. The one in the bag that says positive 10 centimeters focal length might actually be a little bit different from that based on the manufacturing process. So we want to accurately measure what the focal length of that lens is. Now, if you work through the lens equation or if you look at the theory is that if I place a lens in the lens holder here, if that lens is located at a distance from the screen exactly equal to its focal length, then it will take an image from infinity, or a long distance away, and focus a clear image. So what we're going to do is place a lens in the lens holder, move it until we get a clear image here of a faraway object, and then the distance that we'll be able to read off of the scale here is going to tell us what the focal length of that lens really is. We will start with the positive 10 centimeter lens. Sorry for the bumpiness of the camera. Up just a little bit. Okay, so now I have the lens positioned near the screen. Now I need a distant object to focus on the screen. What I'm going to use is the open window, which makes a very bright, visible picture. We're going to focus that on the screen to find out the focal length of the lens. Okay. I'm going to dim the lights for that process. Okay. Looking at the back of the screen, you can see kind of a greenish and a bluish fuzzy image here. That's the image of the oak tree outside and the sky. I'm going to turn around, grab the lens, and I'm going to slowly bring it closer. Let's see, that's fuzzy. That's clearer. That's a little fuzzy. That is, if you can see it there, that is a pretty clear image of the oak tree outside the window. That's about as clear as I can get it. Now, there's a little bit of decision making here as to where exactly the clearest image is. I mean, that's definitely fuzzy. That's clearer. That's fuzzy again. Right about there looks like the clearest to me, but there's a little bit of uncertainty in there. I could move it probably a couple of millimeters to either side and still say that the image is in focus. I'm going to take this because it looks like the clearest position for me. Now the screen, you probably can't read with the lights out, but the screen is at 0 centimeters, and the lens is at 9.1. So on my data sheet, the lens is supposed to be 10 centimeters from the manufacturer. From my parallel ray method, looks like it's actually 9.1. Okay, I'm going to set you down for a moment. Taking out the 10 centimeter lens, and now I'm putting in the, if I can get the silly bag open. Oh, somebody tore the bag. Putting in the 20 centimeter lens. Getting it wrong and skimming it across the table, that's not good. And now I have the 20 centimeter lens in place next to the screen. And of course it's making a blurry image now because that has a different focal length. I'm going to slowly slide the lens holder back. So that looks a little bit blurry. Bring it a little closer. That's clearer and clearer, and now getting more blurry. So I'm going to try and find what looks like the clearest image I can get of the distant object. Now, again, I could go a couple of millimeters either way and not be sure, so there is a built-in uncertainty to this. The lens holder is currently at exactly 19.0 millimeters, and so I'm going to record 19.0 for the parallel ray method focal length of the lens. Okay. The diverging lens does not form an image on the screen. A divergent lens cannot form a clear image on a screen, and so there's no way for me to directly measure that. I have to use the diverging lens in combination with another lens in order to get any sort of a value there. Okay, now I'm setting up the equipment for the next test. We have here a lit target. Let me see, I need to make things a little bit darker, so it's going to be a little harder to see. Yeah, that's probably not going to show you much. Let me put on some low light here. Yeah, that'll give us enough light to see what's going on. I have here an image. When I turn the lamp on, this makes a bright image. It's hard to see the way the phone is clipping the light, but there's a crisscross of black lines on this projector. You can see the light is passing through the lens, and right now it's making a fuzzy out of focus spot on the screen. Now that means there is an object distance between the object here and the lens here, and then we're focusing an image distance to the screen, and that should follow the thin lens equation, 1 over f equals 1 over do plus 1 over di. Okay? In order for that equation to be valid, I have to find a place where this lens focuses a clear image on the screen. So I'm going to move the lens back and forth, and you can see that's blurry, that's clearer, that's blurry again. I'm going to adjust this until right there the lens is making a nice clear image from the object over here. Right? So this is the situation I want. Right now the thin lens equation is describing what's going on. Now my screen is at 0 and my lens is at 26.4 centimeters. So in my table 2, the image distance, the distance from the lens to the image is, what did I say, 26.4? 26.4. Okay. My object is located at 113 centimeters. So the distance between the object and the lens is the difference in their positions. And I didn't grab my calculator, so I'll leave that for you to work out. I'm not going to try and do that in my head. 86.6? I think it's 86.6. Do it on your calculator, you figure it out. Okay? So when I get this DO and this DI, 1 over DO plus 1 over DI should equal 1 over F. From that, I can calculate the observed focal length that I have from this pair of observations. One observation is not enough to get good data, so I'm going to go back to the bench mount. I'm going to take the object, I'm going to slide it forward about 15 centimeters or so. We've still got an image on the screen, but it's a little bit fuzzy. So I'm going to move the lens back and forth. You know what? I'm going to slide this just a little bit more so we get some deviation here. Right about there, the lens is now making a new sharp image. Okay, so this is another setup that produces a sharp image. My screen is still at 0. My lens is now at 29.9 centimeters. So we are forming an image 29.9 centimeters away from the screen. Let's note in this table right now I have the 20 centimeter lens in place. All right, yeah, I've got the 20, all this data is for the 20 centimeter lens. Okay. The image distance, I've got my projector image at 91.2 centimeters. So that object distance is 91.2, and that is distant from my 29.9. So you can figure out what that distance actually is. Am I doing this backwards? No, I'm doing this. Yeah, that's right. That's right. Second guessing myself. All right. Now I'm going to take the object. Going to give it another good slide forward. Lock it down. Again, we've got a more blurry image on the screen, so I'm going to slide the lens. See, that's really blurry. Clearer, blurry. Not really getting a super clear image here. Let me slide this back a little bit. Try again. Oh, look at that. Look at that. Very pretty. Blurry, clearer, blurry. Kind of a long distance here where it looks clear. It's a little bit hard to make the call of where exactly this is clearest. I mean, it looks pretty clear there. It looks maybe a little fuzzier there. Definitely fuzzier there. Okay, I'm going to say that's about the clearest the image gets, but this one, I've got at least a centimeter of uncertainty either way in exactly where I position the lens to get the clear image. All right, my lens now is at 40.3. So the image is forming 40.3 centimeters away. My screen, or I'm sorry, my object is at 80.7. Let's say 80.7. So my object distance is going to be 80.7 minus that 40.3, and you can figure that out. Now what you're going to do is you're going to take these DOs and these DIs, you're going to plug them in to the thin lens equation and figure out what F is implied by each of these measurements. Right? Now in theory, that F is going to match up with the 19.0 we measured with the parallel ray method. We expect this, the average of these is what we get, and so in the lens one comparison, you'll be comparing your focal lengths from here to your focal length measured directly in the parallel ray method. Okay? On to table 2. Okay. Now in table 5, we want to do the same thing for a new lens. So in this one, we're going to do the 10 centimeter lens. Let me go over here. I'm going to take this lens out and put in the 10 centimeter lens. I got to put you down to do that. Okay, I've now replaced the lens with the 10 centimeter lens. Really can't see anything showing on the screen. There's kind of a dim shadow of the equipment. I move it back towards the object. I don't get anything. If I slide it forward though, you start to see that spot appear. It gets blurry, but there's a point in there where you can see those crosshairs on the object. I would say that happens right about here. Only a couple of millimeters of slack in that observation. It's pretty easy to find. My lens is at 11.6. That means my image is 11.6 centimeters from the lens. My projector is at, oh, still at 80.7 where I left it before. So that object distance, 80.7 minus 11.6, you can figure out what that equals. Take the object, slide it forward by a noticeable amount. That image has gone a little blurry. Ooh, but when I draw the lens back just a little bit, I get a nice clear image again. So for the second image, I am at 12.4. 12.4. And my projector is at 61.1. So 61.1 minus 12.4 is my new object distance. I foolishly put the power cord too far away from the projector. So let me move that over. Slide the projector forward one last time. Now you can see it's much closer to the lens. Take the lens and slide it back. You see that's a little blurry. That's definitely blurry. That's definitely blurry. Kind of hard to tell. Right about there looks like my clearest position. My lens is at 19, let's call it 20.0. Image distance is 20.0. And my screen is at 38.9. That's 38.9. That's math minus 20.0. That math I can do in my head. That's 18.9 for the focal length there. Now again, you've got 3 sets of DOs and DIs. That lets you make 3 calculations of the focal length. And in theory, that'll be a perfect match to the 9.1 we measured at the beginning. Okay. Last phase of the lab, we want to see how lenses act when they're combined together. I'm going to have to set you down for this. Okay, I'm going to flip over to the third data page. I've got 2 converging lenses put together. We want to see the object and the image distance for the image they produce. And I know from long experience that this is going to be really close to the screen. If you can see it, That's blurry, clear, blurry. Right about there, it's forming a clear image. Now we want to consider the position. The equations we're using assume that the lenses are actually in contact together and touching each other. We can't do that with the mounts that we have, so we're going to assume that this is acting like the two lenses are right in the middle of where they actually are. So that position is at 9.1 centimeters. So for the two converging lenses, my image distance is 9.1. My projector is at 61.8. So my object distance is 61.8 minus 9.1 equals, you can figure that out. Now I want to put the 10 centimeter with the diverging lens, which is negative 25 centimeters. Okay, so I'm going to take the 20 centimeter out and replace it with this diverging lens. Okay, the diverging lens spreads out the light. The converging lens concentrates the light. So the two are going to kind of work against each other and end up with the combination showing some focal length that I can calculate from the equation. Put that lens in, put them together. Now I've got the diverging and the converging lens, got a fuzzy image on the screen. And slide back. It's a little bit blurry. That's a little bit blurry. Right about there. Looks like I have a nice clear image. The set of lenses is centered around 30.6. So that is 30.6. My projector is at 61.8. Same as before, I didn't move it. So 61.8 minus 30.6 is that object distance. Okay, that's about it. This is, once you get everything set up, this is a pretty straightforward, relatively quick lab to do. That's all of the data taking. So I will leave that there, and as always, any questions, get online with me and we'll talk. Thank you.